Well, it's a real pleasure to be here in Atlanta and to be here in Newcomb & Boyd's office. The first thing that I noticed is the wall of LEED projects here, and there's actually another wall all the way down that hallway. It's a really long list of great projects, and Newcomb & Boyd is just a fantastic firm. We don't have many on the West Coast like this, with one office that does just a wide variety of exciting things. So anyway, it's fun being here, and I'm going to talk to you about net zero energy buildings. And I've been thinking about this for a while. I've worked with a wide variety of clients around the world, around the country. I've worked with academic, private sector, nonprofit, wide variety of folks, and many are looking at energy in a very serious way. And obviously, one of the most exciting and new things that we can do on energy is thinking about net zero buildings. So my history thinking about renewable energy in buildings goes back a long time. I actually worked on the solar hotline for the state of California when I was in college. And this is in the very early 80s, like 80 or 81, something like that. And I just wanted to tell you a little story about solar back then. And remember, there was no internet. And so you couldn't go to the internet to find out about solar. You have to call a hotline, an 800 number. And I was talking to my son the other day, and he's like, well, what's the 800 number? Why would you want to call it 800 number? Oh, because it's free. Well, what do you mean? I mean, aren't all phone calls on the same price? And he didn't even understand why you would want to have an 800 number. But anyway, so on that 800 number, we got a call one day. I got a call. And the person on the other end of the line said, well, I'm calling because I'm looking for a solar clothes dryer. I want a solar clothes dryer. And my engineering mind is starting to ramp up and thinking about all kinds of complicated fans and ducts and solar collectors, like you might see in this photograph, big system. And I said to the person on the line, hold on a second, let me ask the other folks in the office if they know about the solar clothes dryer. And so I put that person on hold, and I told the others in the office, and they all started laughing. It was a joke, right? And I didn't get it. It was like solar humor. The person was actually calling about a clothesline, and I was thinking about a big duck and fans. So it was sort of like a solar prank call. And I got back on the line with the person. They started laughing. And, yeah. So we have to always remember, lesson learned, that always look for the simple solution first. And that's been something that I've used in my engineering career, of thinking about how do we simplify things. And the simple solutions are ones that tend to be more reliable and more affordable. And that's key to making the newer buildings, net zero energy buildings, work. So we're going to talk a little bit about that. I want to start by giving you an update, talking about some of the buildings that are out there and some of the strategies that people are using. The first thing is looking at the growth in net zero energy buildings. The New Buildings Institute is a nonprofit that tracks net zero energy buildings, and this is data from their website. And they are tracking buildings that have actually they have verified as being net zero buildings. They also are tracking the ones that are emerging. And that is buildings that are claiming they'll be net zero, but they don't have enough time yet. Yeah, hold on a sec. And they don't have enough time of operating the building to see. Is that working, the microphone? Yes, no? Okay. We have folks online that are also listening in. So, but anyway, they're tracking buildings that are attempting to get net zero. That is, they've been designed, they just don't have a year's worth of operation. And then they're also tracking ultra low energy buildings, and that is buildings that are maybe not net zero, but are very, very low energy. And you can see it's doubling. And what I've seen when I talk to different folks in green buildings community. There is a huge amount of interest. Can we do this? We want to do this. We want to try to do this. And as you'll see in my presentation, it's no longer small nonprofit organizations that are looking at this. So I did design what is by many considered to be the first net zero office, and it's a small office in San Jose, California, so mild climate with lots of sun. We've got to start somewhere, right? And this is a renovation of an old branch bank. And it was about 10 years ago, and did a very low energy building, put PVs on the roof, and it all worked out. It was great. And interestingly enough, the guy who did this office had a huge amount of publicity. In fact, the governor came by the building, which for a small little renovation building is a very big deal. And a lot of stuff in the media, and that was fun for him. But there's a reason why bigger companies want to do net zero building, because if they get the governor or even the mayor or even a city council person to come by the building and get some free press, that's a good thing. So I also designed the Packard Foundation. This was a more recent building, opened 3 or 4 years ago. Again, still in California. Building, it produces more energy than it consumes. And every year it's been getting better because they've been tuning up the building. And now with the growth that we're seeing in California with the electric cars, they're happy they have a little bit extra because they're now starting to put in some vehicle charging stations that will consume the extra electricity that the building makes. The Bullitt Foundation is one in Seattle, Washington that opened a couple years ago. 4-story building. It's not a hard climate per se doesn't require a lot of heating and cooling, but it's hard climate for solar systems because it's cloudy so much. So you can see a large PV system on the roof that extends out over the edge of the building. And that is net zero. I've had it over a year of operation. Really interesting building. I did the Exploratorium Science Museum, couple 100,000 square foot renovation of a pier in San Francisco. A lot of interesting things. One of the things about that project that we used the bay water with heat exchangers for providing cooling in a radiant slab. Now we're starting to ramp up. That Science Museum is 200,000 square feet. This is 300,000 square feet. The National Renewable Energy Lab in Colorado built an office building, a research support facility, and that's net zero. And it's a combination of PVs on the roof as well as in the parking lot next to the building. Or it's a series of buildings together. So large. I worked on the Venter Laboratory in San Diego, and that's a lab building that's net zero. It's just opened about 8 months ago, so we're starting to get the data now. It's designed to be net zero. We'll see. I think we'll get there. And lab buildings are very energy intensive, so getting a lab building to be net zero is a lot of work, but this would be, I think, one of the first lab buildings to be net zero. DPR Construction, a national construction company, they now have 3 offices, one in Phoenix, one in San Diego, one in San Francisco. They're net zero. Phoenix, obviously, being a tougher climate, and it was a renovation. And in fact, they didn't put any PVs on the roof of this building. They have PVs out in the parking lot, and that was enough. Some shade structures over where people park. It's a single-story building, but designed to be very low energy. And the fact that they don't have any on the roof does make it clear that even in Phoenix, we could get a 2 or 3-story building to be net zero. And Phoenix does have a difficult climate. So we're starting to see developers get interested in the net zero. This project in Sunnyvale, California was developed by Kevin Bates of Sharp Development Company. He is now buying up 1970s vintage office buildings in Silicon Valley and converting them to net zero energy offices. And what he does is he puts the PVs on the roof. He makes the building very low energy through modifications, simple, cost-effective ones. And then he'll sign up a lease where the energy is included. It's a full service lease, so the tenant doesn't have to pay for energy at all. And he's able to, in his first 2 buildings that he's done, lease them faster at higher rates than what the market is doing. So he's finding a competitive advantage by having the net zero building. And really nice space for 20 companies. The whole building, this first building was taken 100% by a single company. They did use the electrochromic glass, small amount of it because there weren't a huge amount of windows in the original building, but it allowed them to downsize the cooling system because the glass was better. They put more insulation in, a variety of strategies to make the envelope better so that the cooling system was smaller and more affordable. And here's the roof. At UC, University of California at Davis, a whole village, student village was built that is net zero through a combination of photovoltaic systems and biogas generated from waste that comes from on-site, mostly the dining, but also some of the plant debris. So they make biogas and use fuel cells to generate electricity. So a combination of fuel cells and photovoltaics, net zero energy village. We're working with another developer on a project, a 2-story office building for it's a developer, and that's going to be net zero on the electric. They still are going to use a little bit of gas, but it's 80% of the energy is electric, and that's going to be offset by PVs. And they were also able to lease up this building very quickly to a high-end national law firm that saw it as a real bonus for their employees. And we're working on a large 750,000 square foot campus where they're still in design, looking at doing net zero. And this is Silicon Valley for large tech companies. And for that company, I just wanted to show you what it looks like now for developers, the PV systems. It has a relatively long payback. So if you have a PV system and you're a developer, the tenants pay for the energy, so why would you buy a PV system? But if you look at it a little bit differently, and that is the levelized cost of electricity. So what's the cost of electricity that a PV system generates? In this case, taking into account the future tax credit, that is 10%, not the 30% that's available now that's going to be phased out, but with a more modest 10% national tax credit, not just California, it's 9.5 cents a kilowatt hour, which is actually cheaper than the electricity that you buy for commercial clients in Northern California. I know it's cheaper here, okay, but just bear with me. And so what he's still offering the tenant is a 5% discount on electricity. He's going to get an 8% return on investment, or $800,000 net present value, and that's just for a 20-year lifetime. The system will probably last more like 40 years. The numbers get much better when you look at the longer lifetime. So what developers are seeing is that slowly but surely in different states, it's starting to make more and more sense. And so I think we're going to see, and this is where the heart of the market is in the developer community, private sector. We're going to see a real growth in net zero energy buildings. In fact, in California, the energy roadmap has by 2030, all new commercial buildings will have to be built to be net zero. And of course, there will be exceptions for tall buildings in San Francisco and LA and things like that. But by and large, the vast majority of commercial buildings will have to be built to be net zero, new construction. So moving really big, Apple has a data center in North Carolina, made in North Carolina, and they have a 40 megawatt solar PV system and a 4.8 megawatt fuel cell system. Covers 60% of the energy use of that facility. So very, very large PV system that Apple has installed. And I'll talk a little bit more about what Apple's doing in a corporate level. So I wanted to briefly summarize what are the 7 steps that we need to follow to get to net zero buildings. And some of you might have seen this, but if you're very rigorous about what can be obvious, then you'll be able to get there. And the first and most important thing is that we want to design low energy buildings and do it without gas. We want to have, for getting to net zero, by and large, the solution revolves around going to electric buildings and generating electricity. And low energy buildings are always going to be cheaper than PVs. Until a certain point, if PVs continue to drop in a even more dramatic way, it might get to the point that even efficiency doesn't make sense. But still, today, with the lower cost of PVs that we have, efficiency is more affordable. So we make buildings more efficient first. And more efficient, we'll talk a little bit about it, more efficient lighting, more efficient building envelope, all those things that make a building more efficient tend to be more cost effective. And simple and straightforward. Second thing is thinking about the occupant and the envelope and creating a more responsive envelope to the building. And that also makes a more efficient envelope. What's going on in buildings today is there's a lot of glass. Architects love glass right now. A lot of developers love glass. And there's a lost perspective of what do the occupants want. And I've talked to some of the brokers, and they're saying that their tenants are saying to them now, don't take us to any more of the glass buildings with big south and west glass walls. We don't want that because our employees are complaining that they're uncomfortable. There's too much glare. It's hard to get thermally comfortable sitting in the sun. It might look nice when the building's empty, but when you have to sit down next to a big window, it can be a big problem. So when we look at the energy impact of these glass buildings, let's compare the Empire State Building to a new Bank of America tower that was built in New York City. And now you can look at the energy data for any large building in New York City. It's available online. It's part of the energy rules in New York City that every building has to report its energy use. Right? So if you look at that data, you'll find that the Empire State Building uses half the energy that the Bank of America Elite Platinum Tower uses on a per square foot basis. Okay? And remember that the Empire State Building did go through a retrofit a couple of years back, so they did improve a lot of the systems in the building to get them to be more efficient. But still, half the energy, and it's an older building. And I talked to a facilities manager, and he said, well, we all know, a facilities manager in New York manages a variety of buildings there, and all of his community in BOMA, they all know, they say, yeah, we know that the new buildings with all glass, they use twice as much energy. It's no mystery. We know that. And so they're seeing that these glass buildings, they use a lot more energy, but they're also less comfortable because of the glare and the thermal problems near the perimeter. So when we start thinking about what does a better facade look like, there's a variety of different ways of doing shading. This is a building that we worked on where the owner said, it's in India, hot climate, very large. This is a 250,000 square foot building, and they build about one of these every month, big software company. They said to the architect, we want 100% daylight in the space, but no direct sun, because it's that direct sun that creates the visual glare on the computer screens and gets people uncomfortable. But we want the daylight because we want low energy buildings. So this is what they ended up with. It's a sunshade light shelf combination. And this is the space during the day with the lights off. And it's hard to see from further back in the room, but it's incredibly pleasant environment. There's no glare. It's just the right amount of light. There's not too much. There's not too little. And it's very visually comfortable. Your eyes don't squint. So very successful. And during the daytime, the lights are off. They're dimmable, but they just go off. We're looking at a variety of external shading devices. This is Packard Foundation Net Zero project that I mentioned earlier. And now there's an electrochromic glass that can change its tint with an application of a small current. That company, View and Sage, there's a variety of different companies that are selling this kind of a product. The price is starting to come down, and we're seeing that going into more and more buildings. So the third thing that we need to think about on net zero buildings is doing LED lighting with controls. And I say specifically LED lighting because it is the next generation of low energy lighting. And we're going to talk a little bit more about that. And LED lighting, the cost is going down rapidly, and the efficacy, that is the lumens per watt, is going up very, very quickly. And it's right now equivalent to fluorescence, and it's going to surpass fluorescence. And 2 to 5 years from now, we'll see LED lighting that's almost twice as efficient as fluorescence. It's already in the lab, already proven, and they're just getting the manufacturing costs down for the more efficient LEDs. Fourth thing is very low energy HVAC, and there's not just one system, there's a lot of different options for making low energy HVAC. One of them is in-slab radiant cooling. I've done a lot of that, even in very hot, humid climates. Chilled beams, the dedicated outside air system, a whole variety of systems are now available that allow us to use less energy in the HVAC system. In this particular case, and I wrote an article about it, it's on my website, ASHRAE Journal, where he took a 250,000 square foot building, cut it in half with the radiant, half with the optimized VAV, and the radiant side and it was metered very accurately in a very detailed way. The radiant side used 40% less energy than the VAV side, and it had the same amount of solar load and lighting and everything, and it cost 9% less to build. And so it's a cost-effective solution. And so now we have a lot of our clients in the U.S. traveling to this building in India to take a look so that they can replicate it here, which is kind of interesting, innovation happening there. But a lot is happening in places like China and India because they're building very quickly and they're trying new things. Some are failing, but some are working, and where there's good lessons learned, we should go learn those lessons. Another part of low energy HVAC is friction. A lot of people don't get it, but half the energy in HVAC systems are friction. That is fans and pumps, and they are there to overcome friction. So we're far from optimized. If you look at the human heart, it's 1.5 watts per GPM. It's a measure of efficiency, and it's with 60,000 miles of blood vessels in our body. It's not that the distance is so short. There's so much going on in our body. The heart's very efficient. But when we do HVAC systems, we're typically in the 15 to 20 watts per GPM. So we haven't really conquered friction in HVAC systems. I could get into that in a lot of detail, but there are very simple, straightforward ways to design systems that have half the friction, and therefore we cut that watts per GPM in half. We're still not as good as the human body, but we're getting there. Fifth thing is on net zero buildings is lower energy plug loads. And what happens when we start getting more efficient lighting systems, more efficient HVAC, is that the plug loads can end up being half of the overall energy use. And that can be an opportunity. You could call it a problem. I see it as an opportunity. So we've been working with a lot of our clients on how do they get their plug load energy use down. And when we did the Packard Foundation project, we did a whole study on all of the things that they could do to lower their plug loads before they move into the building. And one of them is we looked where they were using a computer or a monitor or a printer, is there a lower energy version? And it turns out the Energy Star website lists all the monitors, all the computers, the printers, all those things that are being sold in the US, they're all in a large spreadsheet. So we found monitors, for example, that had the same brightness, contrast, resolution. And turns out the best monitor was Lenovo one, and we said we should buy a Lenovo monitor, and they laughed at us and said, no, this is a Packard Foundation. We bought only HP stuff. So we did look a little bit deeper, and we found that HP did have a low energy monitor, and they ended up buying that. So a wide variety of things, and they were able to, through a focused look at everything that they plug into the wall, they were able to cut their plug load energy in half. And that's part of the reason why the building is exceeding what we had expected, and it's generating more power than it uses. The sixth thing to get right is getting controls to work. Control systems, by and large, aren't working very well in buildings. This is a graph of a valve for hot water that should just be modulating smoothly, but instead it's going up and down, on and off, open and close. You see that everywhere in control systems. And there's a whole industry that has been born to handle this. It's called commissioning, but it's because fundamentally the control systems aren't working correctly. And so there's a big opportunity for new technology, improved technology to come and basically displace what we currently have. So there's the beginnings of that. The Nest thermostat is a little bit of a shot across the bow. It's just a little thermostat, but the folks at Google saw the potential of that $3 billion worth. And so we're all following that, of course. But some of the other startups that are out there, one is called Building Robotics, where occupants are able to give feedback to the system, in essence act as a thermostat themselves and say, I'm too hot, I'm too cold, and it goes through a layer that is put on top of the existing control system that then helps to get a VAV system under control for better comfort and lower energy use. This kind of system, or these types of ideas, are ones that I'm seeing a lot of in Silicon Valley. Another one that I'm involved with is a heated and cooled chair, where you can actually have personal comfort, where everybody gets more personal temperature control and therefore better comfort and lower energy use in the building. A lot of potential with that kind of a thing. We'll see more and more personal comfort strategies out there. And then the seventh thing, last but not least, is leverage the falling cost of PV systems. In the last 15 years, PVs have dropped by a factor of 4. That is from 10 watts, $10 per watt, excuse me, down to about $2.50 per watt. And it's continuing. It's not going to necessarily go another factor of 4 down, but estimates are for the next 5 or 10 years that it will get cut in half from where it is today. Remember in this, well, I remember in the late 70s, PV systems were more like $100 a watt. So the prices have dropped dramatically. The market has changed. It's not what it was 10 years ago. And as a consequence, the installations of PV systems have just been accelerating. And I know that there's been some barriers in Georgia, but those will eventually, you won't be able to hold back a whole market. So eventually there'll be a easier way to do PV systems here. And it doesn't really matter if you're putting in a PV system that's smaller than what your meter is reading. So if you think about a campus environment, right? Some of you here are from universities, and if we put PVs on one building, that's not a problem, even if Georgia Power doesn't want it, because those PVs are going to be smaller than your consumption at all times for the campus. So you won't ever have to feed electricity into the grid. Another thing is that the unsubsidized levelized cost, so the cost of energy generated from PV systems, these are the projections of 2014 of where we are today. So you can see PV is more expensive than coal, natural gas, and wind. But PVs are starting to, their projection for 2025 is that the cost of energy is going to start to be competitive with coal, natural gas, and even wind. So in some parts of the grid in the US, PV systems like California are already cheaper than the grid electricity. Okay, I know you haven't hit that point here because electricity is cheaper here than in California. But I do remember just 10 years ago thinking that will never happen. And it's starting to happen in California and a variety of other parts of the US. So you expect that bit by bit, the nature of the grid and where we get our power is starting to change. In California and some of the other states in the US are starting to talk about the peak, the peak demand for electricity, which is right now in the afternoon on a hot day. That's when utilities struggle to keep up. They're starting to but they're starting to see the pattern change. So the peak demand is going to be in the early evening after the sun goes down. People go home and start turning on all their appliances. So our time of day pricing is going to start to change. The electricity might end up being the cheapest, and this is maybe 10 or 15 years away, but it might be cheapest during the day when there's a lot of solar production. And you'll be taking an electric car to work and be able to charge up at work for half the price if you charged up at home during the evening. Right? So there's a lot of different things. The grid is changing, and it's because of the price of the renewables. So if we look at the projections over time, this is also comparing the natural gas combined cycle, which is the cheapest form of electricity right now in the U.S., to the solar, and looking at looking out to 2025 and seeing it get competitive. So if you look at a map of the U.S., some of you might be interested in this. This is the cost of electricity for the different parts of the U.S., right? So you can see California is high. Arizona is not super high, but higher. Alaska and Hawaii are crazy high. Hawaii, right? So the Hawaii grid is going to be changing. New England. And then you start looking at other places like Florida. It's a little bit expensive. So you don't have the cheapest power here. You're in the middle. And slowly but surely, things will start changing here as well. And utilities won't be able to stop it. They tried to stop it in California, but that was about 20 years ago. Okay, so I don't mean to get political, but this thing of not allowing people to do a solar lease for power in their home, it should be an economic choice. If I want to do solar, why shouldn't I be allowed to lease solar and put it on my roof? So we had a nice discussion about that last night over dinner. But anyway, so here are those steps summarized. And I do personally think that a net zero building is simple. It doesn't have to be complicated, just like our clothesline. If you follow the steps and pull the best practices that other people have done, it's what I call a state of the shelf. We don't need to invent anything new. It's just that we need to put the best practices, all of them together to get the net zero energy building. Okay, so let's go ahead and talk a little bit more about lighting and PV systems. Yeah, I want take this one too.
I have one. My name is Matt DePiro. I'm an electrical engineer here with Goodman & Boyd. I just want to follow up on a few things that Peter's already mentioned, including lighting technology, photovoltaic technology, things that we've seen come through the industry here in the last 3 to 5 years past. So LED technology is a conversation that we probably couldn't even have 5 years ago. This is something that's gone from just lab work to figuring out how to maximize efficiency in these units. 5 years ago, we probably could have seen some screw-in type fixtures or LED tape lights. We also see LED downlights have become prevalent. But nowadays, as of most recently, projects we're working on right now, we're seeing more general illumination type fixtures being implemented, including area lights for outdoor spaces. And if you kind of average all the numbers together, we're looking at a 20 to 25% energy savings over just standard fluorescent, especially linear fluorescent lights that are most common in the industry. We're also starting to see things like athletic venues, where here we have Safeco Field, where the Mariners play. This field has been, or this system has been approved by the Major League Baseball for use in Major League stadiums. So they're seeing benefits not only in performance, but also from a television aspect. They can use LED lights to reduce the flicker that you see when slow motion instant replay is used. LED, as Peter mentioned, it's shot the moon in terms of efficiency goes lately. Here, the most recent numbers are surpassing this red line here, which is about the average of fluorescent efficacy. So lumens per watt is how we measure the efficiency efficacy of a LED module. And you can see that eventually it tapers off as they're predicting up in the 250 lumen per watt range, but we've got 10 more years before that even comes about. I'm going to now talk about how lighting control systems, this is a very crude diagram of how a typical lighting control system works in a building. We have our linear fluorescent lights, we have an occupancy sensor, all of which are tied together with a low voltage control system. This is more of an example of a higher end programmable system that, when incorporated correctly, we could actually zone this thing so that the lights nearest to the windows dim down more than the lights that are further into the space. So you see here that maybe you have a 10% output, a 50% output, and a 100% output in a space that's got a lot of glass. And then consequently, when cloud coverage comes in or you have a gloomy day, then all the lights automatically come back to full output. And this is something that the user doesn't even have to integrate with. Jumping quickly to the future of lighting control systems, we're actually seeing this come down the pipe now, where you will have no line voltage power running to your fixtures. It's going to be all power over Ethernet. I can't speak to the actual characteristics of the system, but it is something that Adam will touch on very briefly as well. Photovoltaics, this is the Georgia Tech Club Commons building where we have, this was finished around 2011. We have an 85 kW PV system on the roof along with some solar thermal hot water heating. This is about 10,000 square feet of roof that we were able to accommodate. And it produces, it feeds back into the building, but it produces a fair amount of energy. Sorry, this was the view from the roof. It's a nice view of Midtown Atlanta. But basics for a PV array is that obviously the sun shines onto the modules, and the modules use a DC low current, which is not current that we can use in a building. So it has to be transformed through inverters in the building. And you can see in this picture here that inverters come in many different sizes. Their size depends on the actual size of the system. So at Georgia Tech, we actually used a handful of these medium-sized inverters. What we're going to do now is just a quick little case study. This is all completely theoretical, assumptive in nature, but it illustrates the point of how we're going to get to net zero through the use of systems like PV. Let's say we have an 85 kW array. It's great for marketing purposes, but when it comes down to it, only 60 kW is actually, on average, probably output when we have sunshine available. These are losses that are seen through the inverter process. So 60 kW for the purpose of this exercise is what we're going to use. We're also going to say that 60 kW feeds directly into the lighting only load. So in the case of Georgia Tech, we actually fed just back into the building. No particular load was assigned to it, but we actually have the metering data. That didn't work. This is the actual lighting load meter data from the Club Commons. This is a month's worth of data. You can actually see Sunday through Saturday. They're very well illustrated, and the average comes out to be about 85 to 90 kW across the board. So for a 230,000 square foot project, it's a pretty good number. Let's say we take that 20 to 25% on average LED reduction, and we apply it to that same meter data. We're looking at 65 to 70 kW on average just by switching from linear fluorescent fixtures to LED. This graph is tough to read, but this is what happens if we attribute the 60 kW on average from the PV system, associated directly to the lighting loads. So the red that you see positive here is the actual lighting that you're paying for. This is the actual lighting that you're getting a rebate from the system, and then the average comes out to be 8 to 10 kW. So just again, on average, this is a system that runs into 60 kW when it's performing during daylight hours. 8 to 10 kW for 230,000 square feet is pretty good. To wrap up, just kind of the net zero with photovoltaic topic, what you see here is a project we did at Emory where we collected rainwater that came down the roof through gutters and downspouts. It was collected in a cistern buried below grade and then pumped back into the building for use for toilet flushing. Here's an image or some images just to kind of illustrate the point, but we used hardscape features here to collect and then divert the rainwater into the cistern. Then with these PV panels, we charge batteries that, when on demand, the system would then pump that water back into the building. It was treated, and then technically this is a net zero portion, or a net zero component of this building now. We'd have to see things escalated quite significantly for this to happen building wide, but just a small example of something that we've done. So that's it for me. I jumped your
Thanks, Matt. Okay, so I'm going to talk about intelligent buildings. What do we mean by an intelligent building, and why is that related to net zero? Well, net zero building really is a high-performance building. And so to make it really high performance, we're suggesting that it should also be intelligent. With all the technology out there these days, it's really, you need to use that technology to the owner's advantage. Okay. So Peter already mentioned that a Nest thermostat is a perfect example of that, where the sensors and the technology out there these days is so smart that it actually can learn. And so the systems in a commercial building translate to that same topic. So you're talking about systems that are designed to learn from what the occupants are doing and what the loads really are, what the functions really are of the facility. Some of you might have heard of the Internet of Things. Well, the Internet of Things is expanding greatly and quickly, and that's because the cost of these devices and the cost of the processing power is so small and getting so small that they're expanding quickly. And so there are experts that predict that by 2020, the Internet of Things is going to constitute 28 billion things. And so the idea here is to translate that to what we're doing in the buildings. You need to use the information that's available and integrate the system so that we can make the information there at the user's fingertips, at the facility staff's fingertips. But there's a process that you need to go through to deliver that. So that we're not just talking about HVAC systems. You have power systems, lighting control systems, water and irrigation systems, security systems, and for some applications such as healthcare, you might be talking about patient tracking systems or looking at people counters, determining how many people are in the building at any given time. It really gets into a conversation about what does the user and the owner need on the back end. To do that, there's a process of determining how do these systems need to be integrated. What are the protocols need to happen, or what are the protocols for different systems? How can they talk with one another? How open are they? How customizable are they? And so we recommend that you go through a process of developing an intelligent building platform. And that process requires a technology consultant, but also requires a champion on the owner's side. They need to understand what are they going to get on the back end, what are they going to use it for, and start thinking about what are the new technologies that are out there. So Matt mentioned that there's a redwood type system or a low voltage lighting system. That system actually comes with sensors that are in the light fixtures. And so you have a temperature sensor and an occupant sensor or a motion sensor and a lighting level sensor in each light fixture. That information then can be fed back to a central database, and it actually tells you not only whether a space is occupied or whether there's people in it or what the temperature is, but even in the different portions of the room, what are the conditions. And that can dictate how are they using the space down the road. Maybe they change, maybe the schedules for the space have changed. It provides a lot more information to the owner over time. So once they have these sensors and everything in place, what does that mean? Well, they need to use the information. And so going through a process of determining what is the owner going to use the information for on the back end, that's very important. What kind of metrics do they want to see? So what do we mean by high performance building? Well, it doesn't just mean delivering what the owner needs. It's not just meeting the project requirements. It's not just a low energy building. That's very important for low energy, but also delivering a low water use building and making it very comfortable. But that doesn't just end at the end of construction. So there's a design process and a construction process, but for a high performance building, it needs to stay that way. For a net zero building, it needs to stay that way for its dynamic life. And so that requires an optimization process that starts at the completion of the project but doesn't end throughout the life of the building. So going through and looking at real-time data and evaluating how are each system performing, also how is the whole building performing, and compared to how we predicted it to perform, and making adjustments real time. And then again, this commissioning and retro commissioning process should not stop at the completion of the job. As far as training, that also ties back into what systems are you putting in. The owner needs to understand these systems. If they're more complicated, they need to be trained for these systems, or it might even dictate going with a more open type platform that allows the owner to make changes over time. The other thing with training is that it also helps if they are open and the owner can make their own changes, they have the ability to hire staff internally. If they're not proprietary, they can hire staff internally to do the work and self-perform the work, which even helps with making things optimized even more. As far as using data, well, that's the main point here, is we're using data to drive the diagnostic process, using temperature readings, humidity readings, occupancy, and then doing something with it on the back end. So once all the sensors and meters are in place, well, what are you going to use it for? Well, some of the hot topics on the market are, obviously benchmarking, lean operations, minimizing your energy footprint, and then performance metrics. So that leads into determining what metrics do you need. So we recommend coming up with a smart operations program that has several steps to it. First, it's a measurement and monitoring process and figuring out what the owner needs. I'm going to talk about that some more in a minute. Having an operations dashboard, using building analytics to help with fine-tuning and also performing predictive maintenance, and then ongoing commissioning and reporting. So a measurement and monitoring plan normally requires the owner to actually rethink the way they do things, not just from an operations standpoint, but also from energy management. So they have to think about what data do they need, what are the metrics they're going to need, and that drives what sensors and meters have to be put in. For example, if they decide in a hospital they want to track patients, then you have to measure the number of patients. If you're going to track energy use per patient, that's a pretty common thing in healthcare these days. Mayo Clinic in Jacksonville is considering that right now. And then as far as dashboards, there's a discussion about, well, how many dashboards do they need? There are different levels of dashboards. So once you have all the data, it needs to be displayed in a way that's very useful to the users and be customizable per the user. So in some cases, it might just be a kiosk that's there for just a general occupant of the building, or in some cases, it might be a building operator. So they might have specific graphics that are there to help them operate the building. And then there will be energy managers, maybe either at the building level or at a campus level, that are looking for metrics to help them track energy use. And this is not just for a matter of energy usage, but also from a matter of tracking when something changes. So when something changes, that signifies that something happened. So somebody should research, well, what happened? And then there is information that maybe even the C-suite folks will want to see. As an add-on to that, there are building analytics software packages that you can add on to it, where it basically takes all this data and performs real-time analysis and identifies when certain things should not be happening at the same time. It'll look at different variables and say, well, these three things should not be happening. Something just happened. You need to go fix this. And it also prioritizes those things. And so what it'll do is it'll say, well, this problem right here is costing you $3,000 a month. Then the owner knows I'm going to go fix that one first because that's the highest priority item. What it also can do is it can say, well, if an energy manager is tracking energy usage and they know that there was a blip, and maybe there's a blip at every time during the day or every time during the week, they don't know why it's doing that. A building analytics package will identify all the things that are happening during the day at that time. And so it will help the energy manager focus in on what's happening so they can, again, focus in on optimizing the building to its maximum potential. So that's about all I had. I just want to wrap up with saying that the overall focus of intelligent building, again, is not to get all the sensors and meters. It's not a matter of buying systems and integrate them. It really needs to focus on what is the owner going to use it for? What are the users going to use it for? To make it really intelligent building and to maximize energy usage. Thank you.
Okay, so I wanted to wrap up with, okay, why bother? Why do we want to deal with this? And I want to just give you a snapshot and why some other people are bothering. Apple, what they've done is they have now a deep commitment to use renewable energy. Right now, currently they're saying 100% of their U.S. operations run on renewable energy. So some of that is on-site, some of it's off-site. We saw the data center, for example. And then 100% of the data centers run on renewable energy, and that's globally. So this photograph above is a photograph of one of the PV systems that they have in China connected to a data center. So what Apple is doing is they don't really need to do this. They could just buy the electricity. They have enough money. What they're saying is it's part of their brand to be identified as a company that is purchasing renewable energy, trying to help the environment. And it's also part of their recruiting new employees. And this is what we're seeing more and more, is that companies realize that the millennial generation, when they're graduating from school, they assume that the company that they're working for is doing the right thing on environmental issues. They don't necessarily, it's not the #1 criteria, but they just want to know the company's doing the right thing, right? We should be doing that. So it's becoming a recruiting thing, and it's not just with Apple. I was at a meeting in New York where a variety of the large building owners in New York City were represented, and one of them said that their tenants, law firms and financial companies, are saying they want the green buildings with green features because their employees want and expect that. So for Apple, it's the brand identification and their employees, those are more important to them than even energy costs. And so a lot of companies are looking at it from this perspective. EPA has a Green Power Partnership, and 78 of the Fortune 500 companies are part of this Green Power Partnership. And on their website, you can go and look at it. But this list is just the beginning of the list. At the top is Intel and then Microsoft. But then there's Kohl's Department Store, Starbucks, Cisco, Boeing, MetLife, Johnson Controls, JP Morgan, Chase. All of these companies are making commitments to have a large part of their energy be renewable-based energy. So these companies are seeing the same thing. It's part of identifying the brand, but it's also part of doing the right thing, that their employees are going to feel good about the company that they're working for. And these are some of the non-energy benefits. So when we talk about net zero energy buildings, yeah, it's a lot of work right now. It might not be the most cost-effective thing, but people are still eager to do it in all the different states. One of the net zero buildings that I didn't talk about is a branch bank in Florida. Again, it's similar climate to here, similar electricity prices, but this TD Bank, which is a very large bank, is now trying to do their new branch stores as net zero. Another thing is that net zero energy buildings are a big market. So we could say, well, that's a hassle, and we said that about LEED, right? Remember 10 years ago, the LEED thing is a hassle. Well, it's also a big market. And one study that Navigant did has the revenue from zero energy buildings to be nearly $4 trillion through 2035. That is cumulative. So that's a big market, and not one that we should ignore in my mind, because not only is it doing the right thing, but it's doing the right thing financially. There's an opportunity here. People want it, employees want it, students want it. So we're going to universities, and there's a lot of opportunity. And I'd like to end and just remind everybody that when I finished school as a mechanical engineer and started practicing engineering in the early 80s, I remember making some calls to people about this new HVAC thing called a VAV box, right? And people were saying at the time, some of the old timers that I was calling, who have since retired, right? They're saying, oh, VAV, that system is complicated, it's expensive, it's hard to get it to work. There were all kinds of reasons why we shouldn't do it. And fast forward to where we are today, well, VAV is the standard and we do it everywhere, right? So same thing with LEED, and I know about LEED in Georgia and all that. But LEED is, yeah, that's a whole other story, right? But what we're finding, contractors around the U.S., it depends on the market, but more and more of them are saying we can deliver a LEED gold building, not platinum, but LEED gold building, excluding the registration costs with USGBC and all that, but design and build a building to the LEED gold standard at no additional cost from a standard building. It's become that easy to recycle building waste, to make a building more efficient. All these things now have become easier now that we've built up the experience in the market. So it's another example like the VAV boxes. I think that the net zero buildings are similar. They're tough right now. They're more expensive, but they're getting cheaper every day, and that's why developers and companies are starting to look at them. And the cost of energy is not the only reason why we want to be thinking about and doing net zero energy buildings. So with that, I'd like to end and just say we can't solve this problem with the same thinking that created it. We need to think outside of the box, and I find that that's the most exciting and fun part of what we do. So thank you very much. We have a good 25 minutes for discussion, Q&A. We really wanted to give a chance to have a dialogue. And feel free to, tough questions are good, but also share experiences of things that you've learned along the way. We'd love to have that too. So. And then we also have some folks online. For the folks online, if you would like to give a question, you can put it into the chat window in the GoToMeeting. And we have a person here who will raise his hand and ask those questions, and then you'll be able to hear them. So, fire away. Anybody? Yeah.
You mentioned reducing the friction energy in pump and fan systems. Have you done anything specifically towards that? Are you just talking about increasing the size of pipes and duct work, or what have you been looking at for that?
Yeah, so there is some information out there about designing low pressure drop systems is what it amounts to, with more efficient pumps and fans off of the shelf, but more carefully selected. For example, I helped to write the best practice guide from Labs 21 about low pressure drop design for laboratory air systems. And that a lot of the concepts that are presented in that are transferable to office building HVAC systems. And I would recommend looking at that. It gives a snapshot into what we're talking about. A lot of it is just simple, basic engineering of designing the ducts to be lower pressure drop. And what we like, and the pipes are the same way. And the general thought is to design smooth pipes that don't use as many 90s and 80s. We favor more Y and 45 to get more smooth pipes, and we try to get them a little bit bigger, not one size, it doesn't need to be much bigger, and then shorter. And a lot of times we end up, if you re-examine how you do layouts, you can end up with less pipe or less duct, especially pipe, and therefore do it in a way that's cost neutral. One of the philosophies that we use when we lay out a central plant is typically it's done is you have a room, rectangular room, and you put all the pumps against one wall and the chillers against another and the towers outside, and then you start laying out the pipes between them. What we like to do is say, okay, let's lay out the pipes first and get the equipment in line with short and what fat pipes. And another way of thinking about it is we're investing in the passive part of the system that is pipe, and so that the pumps and the fans and the variable speed drives and electrical infrastructure can all be much smaller. I did a project where the pump was half the size of chill water. The pumps were half the size of normal pumping, and the contractor was convinced it wouldn't work. So when they flipped on the system and it didn't work, it was a school project. He went running to the principal, and I got a call from the principal. It's been a long time since I got a call from the principal. And went rushing down there. It turns out the chiller was airlocked. And they got the air out of the chiller, and these pumps that were half the size of what this contractor was used to using, they worked great. And in fact, we measured the flow. It had our 20% safety factor was in fact delivered in the flow, and the system worked great. So it's possible to do air systems as well as water systems at roughly half of the pressure drop that we are as compared to what we see typically. Yeah. Long answer to a good question. I think it's really important. People don't focus on friction. If you look at it over the whole U.S. energy scene, if you include automobiles, it's somewhere in the neighborhood of 15% of all energy that we consume in the U.S. is consumed to overcome friction.
I would say, Peter,
Yeah.
I want to sort of add to that. That has implications for the overall design of the building. We need to be careful that we all work together as a team. I'm an architect, for those of you that don't know me. And so in collaborating with engineers and the rest and the owner on the team to make sure that it works. I mean, for example, we did a lab building where we took lower pressure drop as a primary energy saving strategy, and it increased our floor to floor by almost 18 inches. So it was a laboratory building with a lot of equipment. So we need to make sure collectively we all understand the decisions and their implications.
Yeah,
they're good strategies. They're just by the whole team.
Yeah, I actually think that 18 inches is more than the pressure up. The thing about it is that the pressure.
Well, may have been the engineer too, but we won't go there.
Pressure drop is proportional to 1 over the diameter to the 5th power. So if we take an 18-inch duct and expand it to a 20-inch duct, the pressure drop in that duct drops in half. So we're not talking about taking an 18-inch duct and making it a 36-inch duct. Just to be clear, and I'm trying not to be contradictory, because just so you know, Joshua is a great architect. So he's really into green buildings. So small increases in sizes it's one strategy. It goes a long way, but we also are talking about how we do the air handler, pressure drop in the air handler, how we do pressure drop through things like valves and coils and chillers. A lot of the pressure drop is eaten up in that area as well. So it doesn't always have to translate into an excessive amount of extra space, which we all know that's a really hard sell, right? And we found ways to get around that we don't need a lot of extra space. And
You push more towards radiant systems, you go the opposite way. You can shrink that floor to floor.
Exactly. Yeah, and that's one of the ways in a lab. For example, we've moved over to chilled beams where the majority of cooling is happening in a pipe. Instead of a big duct, we need just a small pipe. And now our ducts are getting much smaller. We still need the ventilation air. And so we go from, maybe we're going from a 36 down to a 20-inch, but with our low pressure drop, we're going back to a 24 or a 22, So we were at 36 and we're now at 22 with really low pressure drop. So there are ways to even make it smaller. So thank you for bringing that up. Yeah. Okay, any other questions? Online? Okay, go ahead. Yeah.
I was thinking as you were talking that some of the things that are really important to achieving net zero are things that I think traditionally we haven't necessarily had a lot of influence over, like what kind of computers and monitors that somebody's going to buy, and even just how they're going to operate their buildings.
Yeah.
And so, I'm assuming that setting those assumptions early on is critical, to be able to design around it. And I was wondering if you could just kind of talk through a little bit how you've seen that successfully done, on previous projects.
Yeah.
What does that look like? And especially if it's one where the end user isn't necessarily engaged yet, like in a developer-driven project, how does that get sorted out?
Yeah. So the good news is on the majority of plug load items, it relates to computing equipment. And computing equipment is inherently getting more efficient right now. It's a good thing. There was this problem that we didn't have it, and then everybody started using it. So plug loads did this huge spike up over the last 20 or 30 years. But the move to have more mobile computing and battery-powered laptops and such, and then also more efficient screens, the energy consumption per workstation over the last 5 to 10 years has been dropping fairly dramatically. So an overall setup used to be about 150 watts. Now we're seeing it more in the 40 to 50 watt range, right, for a computer or monitor. So that's the good news, right? That even if we have nothing to do with what happens, things are moving in the right direction. There is a little bit of this compaction that's going on in offices that moves us in the other direction. So those are the first things. The second thing is there are things that we can design into the building even if we don't know who the users are going to be. And in California, Title 24, our energy code, like ASHRAE 90.1, there is a new part of that that says every other plug has to be one that's connected to some sort of occupancy sensor. So when you leave the area, that particular plug goes off. So it facilitates a system where you can, if you want to, put something like your monitor into a switched plug. And that has created a lot of problem in buildings for new construction right now, because this is like a brand new product that they wrote into the code that was almost not available. But I think within a couple of years that will there'll be a series of products that do that are very affordable, because there's a big market now in California for that kind of a product. So there's a variety of these kind of things coming into being. So even if we have no contact whatsoever with the future users, we'll have the ability to get things under control. We don't require a lot of interaction with users to be able to have a big impact. So if there is some interaction, we work with laboratories and data centers and offices and a wide variety of users and help them understand where the opportunities are to lower their energy use and plugs. And they, by and large, have been very well received. Another thing, and I'll end with this, is that if you have a net zero energy building, there is a goal. We want to make net zero, and by and large, tenants, either the organization itself or individuals get excited about making the net zero, so that that will give a motivation to continue to manage plug loads. And achieve that net zero. So that net zero gives a little bit more impetus on the plug load. Yes, it's a good question. Yeah, go ahead. Yeah.
Okay. This might be more a question for Adam, I guess. I was just wondering, is there more concern for? Are there ongoing maintenance? Is there ongoing maintenance and ongoing cost towards using intelligent systems? I would think there seems like there's so much more data. It seems like there's potential for more security risk as far as I don't know, just updating the security for the whole system and stuff like that. Is there anything like that?
I think that's more of a first cost issue that has to be worked out by the technology consultant as far as security. There is definitely first cost with having these systems integrated and have different consultants on board to coordinate it all. But from our experience, the amount of energy the owner can save by going through those processes I talked about is huge compared to the cost of the work.
Yeah.
Just to add on to that, there's also the idea of if you use analytics to kind of do some ongoing commissioning. If you have to have commissioning and retro commissioning fewer times over the lifespan of the building, that can be a tremendous cost saving. So that sort of thing is included in the Intelligent Buildings platform. But as for ongoing costs too, you want to think about if the idea is you're collecting data, and I think as an industry, we're all just kind of getting started with that. You have people like building robotics that's, go comfy. I think they're, working on more applications in the future too. I mean, it's a platform, and I think that it's pretty exciting, the potential for all kinds of applications. So there will be, I'm sure, some ongoing costs, but that's going to go along with either ongoing savings that can be achieved through going through that data and acting on it, and also just by being able to maybe do some cool new stuff.
Can you talk just a little bit about your biogas system? Was there a lot of additional maintenance associated with that, or what is the actual procedure for making that work in the U.S.?
Yeah. So I should have been repeating the questions for the people online, so I'm going to repeat your question then. So the question is, talk a little bit about biogas systems and such. So biogas systems are not as well developed as things like PVs, and they are more complicated. When you have a larger biogas system, it's fairly easy, so fairly straightforward. The landfill generates methane gas, and methane gas that enters the atmosphere non-combusted is much more powerful of a greenhouse gas. So what people are doing is collecting that methane gas, and it's relatively easy to clean and filter the methane gas and get it to the point where it's combustible at this right level of concentration and the whole bit, or usable in a fuel cell. So there are some landfills where they actually combust and generate electricity with an engine type of system. But what we're seeing, and the Apple case is one of them, they're near a landfill. They're using that biogas, landfill biogas, in a fuel cell that takes the methane and breaks it and reforms it. And then they have the hydrogen that works with the fuel cell. So that's how folks are doing it. There's a building that Heinz did in San Diego that's like 100 to 200,000 square feet, and they use fuel cells at the site, but they're buying biogas that's a couple hundred miles away and putting it into the gas distribution network, and they're calling that net zero. There's a lot of folks who go, well, that's not really net zero. But anyway, they're calling it that because they're saying it's a renewable source of biogas. And then last but not least on the biogas, there is a really interesting project in Vancouver called Dockside Green. It's outside of Vancouver, and it's a residential multi-story series of apartment buildings, and they have a large-scale biogas system where they get city waste and digest it. They have this whole digestion, third party owns and operates this digestion system. They generate biogas. It's then piped to this development, and they use it for hot water heating. Really interesting system, and done all at a commercial rates and the whole bit. Although that system right now, with the low price of natural gas, might not be as cost effective, right? So, yeah. Andrew, yeah.
Could you just explain real quick what the process is to either verify or certify?
Yeah, right. So the question is, what's the process to verify or certify a net zero building? And right now, the only full certification that's available is offered by the International Living Futures Institute, ILFI, and their office is in the Bullitt Foundation building that we showed you earlier. And they have a net zero certification that you can do. It's fairly cost effective, not very difficult, not very expensive, and they'll give you a certificate that says you're a net zero building, and they want to look at 12 months worth of usage data, and when the building's occupied, and just verify. So it's a very easy process and fairly straightforward. That's the only one that's a full certification that I know of. Yeah, in the back.
So I'm curious your thoughts, experience with solar thermal versus PV that barely came up in passing in the presentation. So it's been my understanding that on a per square foot basis, it's significantly more efficient than PV. Am I wrong about that, or can you just share your thoughts on that?
Yeah, so the question was, what about solar thermal? And isn't it more efficient than PV? So depending on the climate, solar thermal can be somewhere in the neighborhood of 60 or 80% efficient on an annual basis, converting sun into heat. And again, it depends on what temperature. Where solar PV systems are typically in the neighborhood of 15 to 20% efficient. So solar thermal is more efficient. The problem with solar thermal is that it's harder to store. Right now with the photovoltaic system, I can, in most states, run the meter backwards and do that to a large degree. And so my storage is the grid. And in fact, I can generate a lot of extra photovoltaic electricity in the summer and then use it in the winter. So I have a battery that lasts, 6 months. Whereas solar thermal you're limited to a tank size, and to get a couple days worth of storage, it's just to have a footprint. So that's like the number one reason. So if you think about solar thermal, it is relatively cost effective. In some states, there's even incentives. But if you use it for something other than a use that you have every day, and a use you have every day is showers or clothes washing, like if you think about dorms or restaurants or laundry facilities, these are facilities where solar thermal, there's a year-round use for it. Although, you think maybe a university dorm isn't at the best because a lot of the dorms get emptied in the summer. And that's when you generate the most, and you can't do anything about it. So anyway, those are the uses that are the best. Sometimes people put solar thermal systems on buildings for space heating. And it can work fine on the sunny days and even last for a day or two after. Okay, that's good. But then, and places like Colorado can be cold and sunny at the same time. But then in the summer, what happens is you generate all this extra heat that you can't use. And there's nothing to do with it. You could put in an absorption chiller or something, but now we're talking lots of money and complexity. For those reasons, the solar thermal does not have as much traction. Its applicability is much more limited. And cost effectiveness, because there's not as much cheap storage. That is the grid. So that has a big impact. That's why you see the difference. Yeah. A lot of net zero buildings will have a few solar panels to handle the solar hot water load. Yeah. That's a good question, though. Yeah. So I think we have time for one more question and then wrap up. Anybody? One more question? All right. Okay. Sure.
Sorry, I guess I get two today.
Yeah. All right. Well, we'll go two more. Whatever.
I liked what you said about windows and making sure that they're not too big, because that can create problems. And it seems like that the question of how big windows should be is really, it seems like it's a struggle between the engineer and the architect. One wants more and one wants less. Do you see that as a discussion that's changing now? It sounds like instead of just more, we're looking at, well, what do we really need? Because really, from an efficiency and energy usage point of view, the less windows, the better. A wall has much better insulation capabilities than a window. There's less solar load. So really, in terms of payback, that's the fastest payback thing that you could ever do is reduce your window area.
Yeah. So the question is about what about windows and what's the right amount and all that. I think there was a pendulum that swung in the direction of what the engineers recommended, and that happened in the 70s and 80s when there was a heightened awareness around energy. And what we ended up with are a lot of buildings with really small windows or super reflective windows and all kinds of weird solutions that created buildings that are very uncomfortable and unpleasant to be in. And so I'm not looking for the pendulum to go back to that place, because ultimately we want buildings that feel great to be in, that we can really enjoy. The problem is the pendulum right now is swung in the other direction, which is way too much glass. And so I think there's a happy medium. And when I'm talking to architects about it, I like to show them different buildings where the glass on a percentage isn't really high, but you go into the building and you feel very connected to the outdoors because the glass is well done. Its placement is just right. There's a right amount at the right locations. Another thing that happens if the glass is not shaded properly, everybody brings down the blind. So you could have an all glass building, you don't feel connected to the outdoors because there was no thought about glare and all the blinds are down, and so you're not connected to the outdoors. So I think there needs to be an awareness of a little bit more sophisticated awareness of how glass works. And I think there are architects out there that do get this. I think that perspective of a more balanced look at glass is where we're headed. I see slowly but surely architects, a crack starting to develop in the all glass mentality. I was at a meeting with Gensler the other day, Gensler being a national architecture firm, and one of their top principals said to me, well, the era of the all glass building is almost over. Like I didn't ask him to say that, I didn't prompt him, he said it, and I was like, wow, this is the beginning of the end of the all glass building. So anyway, we'll see where it ends up. But I think it's a style right now. And I think people want glass. People want to be connected to the outdoors. But we need to get a little bit more sophisticated about how we do it. Right? That's what I see happening. So if you're involved with a glass company, don't worry. We're still going to want glass and be connected outdoors. So. Yeah.
Oh, just a quick comment about you talking about the solar system. I think in buildings that aren't shower driven, it's easy to overestimate that. So I think you spoke to that just right sizing of the need. But yeah, what I wanted to ask you, but one of the last slides you showed was revenue based on net zero buildings. Yeah, if you could pull that back up, just explain where that estimate's coming from.
Yeah, so I personally did not. I just found this study. And Navigant is a well-known consulting firm that I trust them. So I don't know the details of it, but we could look at it. I could find it on the internet. But it's a cumulative. It's not an annual number. So between now and 2035. So think about it. They're including California, which in 2020 switches over to all new construction. So net zero, right? So you could say all new commercial construction in California from 2020 to 2035. Well, that's in that number.
The actual building of those buildings.
Yeah. It's not the PV system. This isn't the PV market. This is the net zero energy building market.
This is okay. So this is actually the cost of the building.
The construction costs. Yeah. Okay. So it actually does, in my mind, and it's again, it's not annual. It's cumulative. It does actually make sense. It passes a squint test. But I don't know the details of the numbers. Yeah. Just being honest.
Right.
Okay, great. Thanks, everybody.
I want to thank everybody for being here, and I'd like to remind you again that if you drove here at Park, we get some parking passes for you. Thank you again for being here, and if you had parked here, we get you some parking passes for that. For those who want to share today.